Let's, I'll tell you what, one thing we did last class was we learned about the tangent, the unit tangent vector, and it was kind of a complicated formula. I don't think I'm really going to redo this, but this was in 12.4. I want to make a point, and then maybe I'll move on to 12.5. But so these were in your notes, and these were these formulas. So you don't. But I'm just reminding you that we learned how to find the unit tangent vector, and it wasn't all that hard. It's r prime divided by the magnitude of r prime. It wasn't that difficult. What got a little more difficult was finding that unit normal vector, because it was t prime divided by the magnitude of t prime. So that took some work. And then I felt like I needed these. It seems to me the real discussion is kind of about the tangential component of acceleration and the normal component of acceleration, which I defined as the acceleration or dot product, the t vector from above. And the normal component of acceleration is a dot n. So it's like if we're trying to find the tangential and normal components of acceleration, what I guess I'm implying is that you need t and you need n. And so we had to struggle through all that hard work to kind of get to here. My point is that I'm trying to point out today is that there are other formulas. I use these. I easily memorize these. But there are some other formulas, and a mathematician might try to go through and prove these to you. I tend not to do that. But I can tell you this. Another way to get a sub t is v dot a over the magnitude of v. Now, I can't really see where that's coming from. Wait a minute, maybe I can. Isn't v just r prime? R prime, and then that's the magnitude of r prime, and so isn't really that just t? That is just t. That is v in the magnitude of v right there. Okay, so I do see that one kind of clear. But all right. So I was going to say you can get at without really finding t, but I don't know. Basically, there's t buried in this formula. But you can get at with v and a and so forth. What about this an? Do I have to? I mean, it was hard to get that n. Okay. So are there alternative formulas to this? Yes, there are. I'll look in the book because I don't have them memorized. Oh, here it is. V cross a over v. Wow. Look at this. V cross a, magnitude of that over the magnitude of v. That's kind of interesting. The real point is you don't have to go get n in order to calculate this quantity. I guess you can calculate it with v's and a's. I mean, again, you don't have to memorize these formulas, and I'm not asking you to prove them, and I'm not proving them to you. Here's another version of this. This is interesting. The square root of the magnitude of a squared minus little at squared. You know, that's kind of a Pythagorean theorem thing. Listen, let me remind you of something here. So what our discussion we had the other day is I played this. This was a fun game to play. If you're on a curve, you're traveling this way, you could have a unit tangent vector. And you could have a unit normal vector. And those are both 1 unit long. They're unit vectors. They're length 1. And then if I walked up to you and said, and what we learned is how we can express the acceleration vector in terms of t and n instead of I and j. Instead of horizontal and vertical, I can express the acceleration in terms of how much tangential is it and how much normal is it. And I'll just make up a problem like this. If I had negative 2t and 3n, I mean, this is an acceleration vector, and with that t and n on there at that point, I could draw this acceleration vector. I'll try. It is, I will go -2 tangentials. By the way, that -2 has nothing to do with left or right or up and down. It really doesn't. That -2 has to do with opposite the tangent vector's direction. Now the tangent vector happens to be slightly to the right. I need to go opposite that 2 units to the left. Or, shit, not left, sorry. Opposite the tangent vector. 1, 2. And then I need to go 3 units in the ends direction. And there's a picture of n, so I would try to do 3 of those. This is supposed to be, that's a little better. And then 3 of those. There's 1, 2, 3 of those. Now look, this distance is little at. That's this distance. This distance is little an. But here's the acceleration vector. It's -2 of those and 3 of those. Here it is. Here it is. The acceleration vector. So there is a right angle here, and so there is a Pythagorean relationship here. Right? You see it? Little at squared plus little an squared is the magnitude of the acceleration vector squared. You guys okay with that? A right triangle with a hypotenuse and a couple of legs. And what was I trying to say? That was that's where this formula came from. An is the square root of the hypotenuse squared minus that other leg squared. If you solve for an, that's where this formula comes from. So 12-4 formulas, you don't have to memorize them, but you might want to try working with them. They're tough. They're kind of tough to work through a problem. But I guess I'm trying to find ways to make it a little less tough. Can you get AT and AN? Can you get AT and AN without capital T and capital N? And it looks like there might be some ways to do that. Yeah. By the way, though, usually the book might, and I might ask for all this stuff, so trying to avoid T and N is missing half the problem. I mean, I'll probably make you find T, make you find N, and make you find these guys, but if you're just looking for these guys, then you could avoid some of that work, perhaps, over here. So I don't really want to do another 12-4 problem today. I could ease into 12-5 unless you guys found a question. Anybody find a question they want to ask me anywhere? All right, well, I'm going to ease into 12-5 with, and that's good because we are taking the day off Monday, so it might be good if I push ahead a little here. Listen, 12-5 is kind of a new topic. The topic is called curvature. And actually, there's another topic in there too that relates to curvature. There's a topic called arc length. But let's talk about this curvature first, and then I'll get back to the arc length maybe. Curvature. Curvature is represented with this capital K, and there's several formulas for curvature. That's one of the reasons I'm going to give you a bunch of formulas for this chapter, because curvature has a lot of formulas. Depending on the situation you're in, there's a lot of different formulas for curvature. But let's start with this kind of basic idea of a formula, which is this. Curvature is 1 over r. And I'm going to say where r is the radius of the circle of curvature. So when you have a curve, you can measure its curvature. Now this is a this is a good instinctual thought about curvature. Watch this. So there's a curve. See that curve? All right? If you want to find the curvature at a certain point, then according to this formula, which is a very primitive, basic formula, I would need to sort of think about the circle of curvature at this point. Now, I don't know if I have that circle of curvature idea very well defined, and I don't think I need it too well defined. I mean, it's kind of tricky. It's kind of like the best fit circle that best fits the curve at this point. Maybe I could get into a tangent line discussion or something like that, but it's tricky. The best fit, the circle of curvature is loosely defined. I'm just going to loosely say that it's just kind of the best fit circle that fits here, that fits the curve at that point. I know it's a little weird, you guys. The point is, does that look like kind of a big circle? It's kind of a big circle. It's kind of got a big radius. And if it has a big radius, then the curvature is rather small. Thank you. The relationship between curvature and the radius of the circle is this reciprocal relationship. And so when the radius of the circle is big, the curvature is rather small at that point. As opposed to maybe over at this point. At this point, you might try to draw a circle of curvature, and it's whatever that best fit circle kind of idea means, but whatever best fit circle fits the curve at that point. Anyway, it's a smaller circle with a smaller radius. A smaller radius would indicate more curvature. Thank you, bigger curvature. Right. It's got this reciprocal relationship, and you can see that. There's curving more at that point. There is a better definition of curvature that involves the arc length. So then I got to get into the arc length. I'm going to hold off on that discussion. I want to show you my favorite formula for curvature. I know we're in this section in this chapter where we're discussing vector valued functions. And so we're discussing vector value. Everything we do is messing with some position function, r of t, a vector valued function. But when you get to the curvature topic, it's kind of fun to regress back to good old y equals f of x. It's kind of fun because it makes the problems a little easier. And if I go back to good old y equals f of x, the curvature at any x is this formula. The absolute value of y double prime over 1 plus y prime squared, that whole thing to the 3/2. Maybe you can tell another reason why I'm giving you formulas for this chapter. You know, I'm not asking you to memorize all these obscure formulas, but that's it, man. That's a nice one. That's a curvature formula. Apparently, the curvature is never a negative number. It's a positive number. It's a measurement of how much we're curving at a particular point. That absolute value is going to guarantee that I get a positive result. I think all this is a positive result guaranteed here. But that's the formula when you have y as a function of x. Let's try this for somebody. Let's just try an example. Let's find the curvature. So I guess maybe two things. Find the curvature function in general. That would be the curvature at any point x. But then you could also find the curvature at a certain point. Find k when x is 3. And my function I'm giving you is this function. F of x is I'm sorry. Let's try this. X cubed plus 2x squared minus x plus 1. I just made this problem up. I'm not sure if it's the best problem, but you can do it. Well, I want to find the curvature. If I want the curvature, I want that formula. If I want that formula, I need a couple derivatives. Yeah, thank you. So f prime is 3x squared plus 4x minus 1. Huh. That's not okay. And f double prime is 6x plus 4. Okay, well, then in general, my curvature formula is, in general, it's the absolute value of 6x plus 4 over 1 plus the derivative squared. Wow. What is the derivative? There it is. 3x squared plus 4x minus 1, that whole quantity squared, and then that raised to the 3/2. There's my curvature in general. Hey, sometimes it's interesting to take a look at the graph of the curvature function. It's interesting. You might want to see when the curvature is a max, when it's a min. That's a little bit of a challenge. I didn't really mean you had to do that right now, but it's a bit of a challenge to type this in your calculator, to look at this graph. Just a bit of a challenge. You're sophisticated math students. You can handle it. You need to find your absolute value button, though, and try to embed all these parentheses, and maybe even put this in parentheses. But it might be worth looking at the curvature function. But anyway, this is the curvature in general to this function at any point. What did I ask for? I wanted the curvature, what did I ask for? Oh, when x is 3. I'm not sure if that's an interesting place or not, but I asked for it, so let's find it. When x is 3, the curvature is some number. It's a number. 18 plus 4, 22 over, oh my goodness. Yeah, plug in a 3, please. 27 plus 12, 29 minus 1, 38 squared. Jesus, 38 squared plus 1. Raised to the
445.
3/2. Thank you. 38 squared plus 1. You said 1445, and then that's raised to the 3/2. So 1445 raised to the 3/2. You know, at some point I'd like to decimalize this and see what the curvature is. It's probably pretty small. What did you just say?
4 to the negative 4. 4 times 10 to the negative.
4 times 10 to the negative 4th. Is that what you're saying?
Yeah, yes.
Okay, thank you. So that, let me just write that differently. 0.0004. Is that what you're saying? I think that's what you're saying.
Yeah, 0.0004.
Okay. Hey, super small curvature. Super small curvature. You know, I was thinking of graphing this function, but you know, it's a cubic function, you guys. You should, you know, I mean, it's a cubic function. You know, except for a couple of interesting places, a cubic function looks awful darn straight, doesn't it? Except for its curvy spots. Except for its curvy spots, a cubic function can look awful darn straight. So apparently my x equals 3 is somewhere over here, and what's the curvature? Not much. You guys okay? Mm-hmm. Did anybody, do me a favor, let's, I mean I can do it myself, but did you graph the curvature function? Did you try it?
Yes.
Okay, good. Did you also try, will you do this for me? Graph the original function, maybe on top of the curvature function, or?
I checked the paved one and gave it.
Yeah, you got it. Okay, hang on. Hang on a second, don't move. So he's got this picture. He's got this picture. Oops.
Oh. Go back to the graph.
Yeah, okay. So that cubic function is roughly this. Okay, you guys? Roughly that is the cubic function, roughly that. It's a little off. So check this out. This is the cubic function. And anyway, when I asked you to find the curvature when x was 3, yeah, I sort of predicted right that x equals 3 was way over here. And anyway, the curvature is not much, right? For the millionth time. Hey, so where is this function the most curvy? And it turns out maybe that's a concept. Maybe yeah, it's most curvy at its mins and maxes, at its relative mins and maxes. That's where it's going to be most curvy. And when you drew a picture of this curvature function, like I said, it's a challenge to get this typed in your calculator. But when you see it and lay it on top of this, it is interesting. What you see is... Now, hang on a second. Here's a concept for you. What's the curvature of a straight line?
Constant.
How much does what is the curvature of a straight line? I mean, we could do the math, but this, I'm thinking, yeah, how much does it curve? Thank you, it's 0.
It goes around here.
That's true.
Keep going.
Depends on which geometry you're in. You're right. Straight line on a sphere. Yeah. It's a circle. Yes. So, when this guy is very straight over here, his curvature is small. When does his curvature reach a max? Probably right about there. This is curvature reaching a max. In between there, it gets pretty flat and straight again. In fact, at an inflection point, it's like you're almost like a line for a brief instant. So wherever that inflection point is, it drops towards 0 again. Might even touch 0 there. I mean, when is this 0? When is this 0? When the numerator is 0. When's that numerator 0?
No, but wait.
Negative 2/3?
Mm-hmm.
Negative 4/6, negative 2/3. So at negative 2/3, that's probably where that inflection point is. It hits 0 at that. The curvature is 0 at his inflection point, I guess. The curvature gets a little more curvy over here, so it probably hits another max right around here. And then it all gets awful straight. If the graph is straight, the curvature approaches 0. So this is a graph of the curvature function laid on top of this function. That's good. That's good stuff. I didn't really know I was going to stumble on that the very first day of 12.5, but that's good. Usually I make you investigate some homework a little bit before that pops up, but that's good. If we wanted to actually find the point where we have max curvature, which is a common question, it's a good question. When do we have max curvature? You know, you could prove it with calculus. How do you prove when curvature is a max? How do you find a max or a min in calculus? Cal 1, you stop the video.
Stop the video.
In calculus 1, when you want something to be a max or a min, you take the derivative and set it equal to 0. Yeah, right. When the derivative is 0, you usually have maxes or mins. So you could prove when this is a max or a min by taking his derivative. Anybody want to take his derivative? You need and set it equal to 0 and solve it, but you could prove when it's a max or min. If you have those questions in the homework or on my test, I really want you to use your graphing calculator to find when it's a max or a min, to tell you the truth. That's what I'd like you to do. When the curvature is a max or a min, which we said might happen at the... Yeah, by the way, not a min, not a min. I'm interested in when the curvature is a max, actually. The curvature is a max at the relative mins and maxes of the function, probably. Yeah. But you could type it in and use a feature on your calculator to find where that is, I guess. Okay. Yeah, there's a lot of cool problems to investigate. Let me, I'm going to back off this topic though. Well, just for fun, again, I'm giving you these formulas, so I don't even see the point of writing them down actually, but just one more time. If you want curvature and you're dealing with vector valued functions, which we are dealing with, the formula gets a little tricky. I don't think I quite have this one memorized. It is, wow, check this out. Yeah, it's r prime of t cross product r double prime of t, the magnitude of that divided by the magnitude of r prime of t cubed. Thing. Yes. So there's another formula for curvature when we're in the setting of vector valued functions. Which is, you know, you might have to do some of that for homework, but I sort of told you, I kind of like, when we get to this subject of curvature, I kind of like to resort back to good old y equals f of x and mess around with that topic in this setting rather than in this setting. But either way, we should do both. All right. So that was good. 12.5 has this big topic of curvature, but and it relates to the normal component of acceleration. I mean, this curving relates to that normal component of acceleration. I don't know if you remember that from the other day. But here's another thing. The way 12.5 really opens is it opens with this idea of arc length. Arc length. And they refer back to chapter 10 and they say, hey, do you remember arc length in parametric equations? Anyway, I'll just tell you what it is. Arc length in parametric equations was the integral from A to B. By the way, we use the letter S for arc length. That's the letter S there. It's the integral from A to B of the square root of x prime of t squared, y prime of t squared. And now that we're in maybe 3D, we would have z prime of t squared with respect to t. So there's the formula for arc length of a space curve. The arc length of a space curve. But maybe you can see this. I'll just, a shorter way to write this, of course, it's the same thing, but when you have x prime, y prime, and z prime, and you're squaring them and taking their square root, aren't you just really doing this? The magnitude of r prime of t. Does that make sense to you? Might depend on how much homework you've done, but you know that. You know, if you took r prime, you'd have x prime, y prime, and z prime, and if you wanted his magnitude, you would throw that in a square root and square, right? Good. So this is this. The magnitude of r prime of t. That's arc length. Let's try it. Let's do one. Let's try this. So I want to find the arc length. Watch this. I want the arc length of one revolution of this curve. 4t, 3 cosine 3t, 3 sine 3t. That's too many dang threes to tell you the truth, but that's okay. Does anybody know what kind of, this is a space curve, as you can tell. It's a curve in space. I want the arc length of one revolution. Apparently it must revolute. It must revolute. What,
It's gonna be a circular.
yeah, this is a good old helix. Yeah, we messed with this in 12.1 a little bit. We need to visit it often during this chapter, I think. This is a helix. It's got this circular motion in the YZ plane, but it's kind of coming out at you, I guess, in the X direction. Good. It's got a radius of 3. That's that 3. What's its period? Its period is 2 pi over 3. I'm sorry that that's this 3. That's the problem with having too many 3's, but you guys got it. That's the period. So that's the time it takes to do one revolution. So I needed that thought to answer this question. I want to set up an integral, I guess. And I think to get the arc length of one revolution, I think I'll integrate from 0 to 2 pi over 3. And what am I integrating? This. Yeah, I need the derivative and I need the magnitude of the derivative, and then I'll integrate it, right? It's actually quite beautiful how this works with a helix, though. Watch how it works. R prime is pretty easy. R prime. 4. Thank you very much. Derivative of cosine. So -9 sine, -9 sine 3t. 9 cosine 3t. Okay, cool. Now what do I want? Oh, I want the magnitude of that. Okay, check this out. The magnitude of that. Hey, after I get this magnitude, I'll put it in my integral and do it. But let's just do it, the magnitude over here on the scrap paper here. The magnitude of that is the square root of, this is awesome, you guys, 16 plus 81 sine squared 3t plus 81 cos squared 3t. And you play the game. Again, if you've been doing some homework, you've probably been running into this game occasionally. You play the game where you factor out that 81, and when you factor out the 81, just out of those two terms, you're left with sine squared plus cos squared, which is 1. It's a multiplied 1 times the 81, and then the 81 is plus the 16, so I'm left with the square root of 97. And guess what? I want to integrate the square root of 97 with respect to t. I want to integrate the square root of 97 with respect to t. So it's just a number. When you integrate with respect to t, you get the square root of 97 t. And you evaluate from 0 to 2 pi over 3, and you plug in 2 pi over 3, and this is a beautiful number. This was my number when I played high school football. That's the arc length of one revolution of this helix. If you put a tape measure on this helix, that's its length. One revolution of this helix. You know, roughly that's 20. Is that what that is? Roughly a 20?
Is that just the circumference if it's one revolution?
Well, circumference works. It is a helix, so it's
Oh, helix. It's still one
so
revolution.
when I say one revolution, it's not connecting back to itself.
Yeah.
We said it had a radius of 3.
Okay.
it's probably coming out at me. It's probably going around once, and then it shows up back here.
Yeah, alright, so that's not.
And when it does, it's out a certain distance here. It could do another revolution, and it would be out here. But anyway, I just wanted the one revolution arc length, and I'm saying it's roughly a 20. 22.63. Okay, thank you.
So the arc length of one revolution, not just a circle, would just be the circumference.
That's true. The arc length of a circle is
Would be,
one revolution of any circle would be basically a circumference. Yes, yes.
20.
Oh, not 22? 20?
Yeah, 20.
Okay, thank you. 20.63. Cool. You know, that's good, you guys. It's not a big deal. It's arc length. I'm going to keep talking to finish a couple thoughts. They do this other thing. They do this. They call this the arc length function. Watch this. This is so subtle and different. Subtly different. It's the arc length function. So, of course, when you find arc length, you're going from a certain point to a certain point, and it's a number. Okay, the arc length is a distance. It's a number. Well, the arc length function is s of t. And the way we get a function of t is, instead of integrating from a to b, we integrate from 0 to t. So we stop at some arbitrary t. Well, some variable t. And then we do this integral. Now hold on, it's sloppy mathematics to put this variable t. If I'm putting t as a bound, I need to use a different variable in here. So we call this u here. So we'll integrate with respect to u. The variable will be u, but at the end, when I evaluate, what do I plug in for u?
G.
I plug in t. You follow me? And I'll have a function of t. And it's not really right to have t's in here and then plug t's into t's. So we change this variable just for this purpose. All right, so watch this. So if I wanted to find the arc length function for this, what would I do differently? Instead of a specific integral from 0 to 2 pi over 3, I would go from 0 to t. Well, that means I got to change this to a u. I would go from 0 to t. Sorry. This would be a u, and I guess what I'm about to plug in for that u? A t. And so I get this arc length function relationship. What I get when I plug in that t is I get this. S is the square root of 97 times time. So now wait a minute, this is particularly on this particular curve. But on this particular curve, for every unit of time that goes by, you travel this much distance, apparently. I mean, if you travel around this curve for 1 second, how far have you gone? Square root of 97 feet. If you travel for 2 seconds, you plug in a 2, and how far have you traveled? 2 square roots of 97 feet. So then they do this thing. All chapter, we've been talking about these vector valued functions, and their parameter is t, and we like to think of t as time. But they do this thing. Once they get a relationship here between t and s, then they can change the function they can reparameterize the function in terms of the arc length parameter s. So, watch this. This is a decent question, but it makes you go through this arc length function. You get the relationship between arc length and time here when you go through this arc length function. You get the relationship between arc length and time, and then I'm saying, here's what I'm saying. reparameterize, I don't even know if that's a damn word, reparameterize the function in terms of the arc length parameter s. And watch what happens. I mean, it's easy to do. Once you've found the relationship between s and t, this is s as a function of t. What is t in terms of s, please? What is t in terms of s? Thank you. S over the square root of 97? By the way, that isn't s. Sometimes it looks like a 5. It's an s. S, that's t. That's the relationship between t and s. Well, then guess what? If you want to reparameterize this curve, go replace all those t's with that. And what you'll have is the same helix, the same vector valued function, but it's going to be in a new parameter, s. And it's this. Three s over the square root of 97, comma, 3 sine of the angle 3s over the square root of 97. Are you guys with me? I've reparameterized the curve, or the function, or the curve, in terms of its arc length parameter s. I don't know what real good that is. You know, if I asked you this question, hey man, you're on this curve. Where are you after you've been traveling for 10 seconds? I guess you would plug a 10 in here and tell me where you're at. Watch this question. Hey, you're on this curve. Where are you after you've been traveling for 10 feet? Then I think I just gave you a distance, and I think you'd plug a 10 in here. This parameter is time. This parameter is distance traveled. So again, 2 questions. Where are you? And that's location. That's X, Y, and Z. Where are you after traveling for 10 seconds? Plug in a 10 up here. Where are you after traveling for 10 feet? Plug a 10 in here. By the way, they're someplace different. It's not the same place. Unless s equals t. Do we have a relationship where s equals t? No, we don't. No. Listen, just to tie this together here, and we're getting toward the end of class, but I'm going to... So, the book opens, in 12.5, they open with this discussion. And then it leads them to curvature, actually. But that's not the way I did it. I walked in and told you about curvature, then it backed up and told you about this. But the connection is this. Their very first definition of curvature is this. Watch this. The first definition of curvature they give you is this. Curvature is the magnitude of dt ds. See, once you change the parameter into s, all these functions, I mean, all my formulas, you know, I've been dealing with all these formulas that have r of t. Well, guess what? Now I can have r of s's. And it means something. It's not just some other, s is the arc length parameter s. And so I can talk about r of s, I can talk about r prime of s, things can be parameterized in terms of s. Well, apparently that's what's going on here. I must have some curve that's, and they want me to take the derivative, let's look at this. The derivative of the unit tangent vector with respect to s, the arc length parameter. Take that magnitude and call that curvature. To me, that's not a very functional definition of curvature. That's why I introduced curvature my own way with those other formulas, right? So I don't know if you'll ever use this formula.
Did you say that k is just the ratio between time and distance?
No, K is curvature
Oh, curvature.
of a curve at any point. But, so I don't think this is very functional, but I want to just finish explaining. I want you to listen to this. Listen to this. Watch this. So what's going on here? We got a rate of change of a tangent vector. Okay? Well, a tangent vector is a unit tangent vector. So how long is it? 1. Okay, so when we talk about it changing, guess what? Ain't changing.
Magnitude?
Its magnitude is not changing. If it's a unit tangent vector, then it's a unit tangent vector. So the rate at which the tangent vector changes is not about how the length of the vector changes. It's about how the direction changes. So this is all about the direction of this tangent vector. This is hard to talk, isn't it? It's the rate at which the tangent vector changes, which amounts to it changing direction. And we want to do that with respect to how far it's traveled. S, length traveled. So does it change a big direction? Is there a big direction change in a small change of length? And if there is a big direction change in a small change in S, then that's big curvature. I mean, I'm trying to help you read this and make sense. And maybe I did. But it's not, like I said, I don't think we're really going to work with that much. I do like this question. But it was pretty easy. It was kind of easy. Reparameterize the curve. Well, it's 12:50. Today's our early day. You want some overtime? I'll work overtime for tips. No. No, I don't know. We're done. I'm giving you my explanations of these chapters and these concepts. At some point, it's cool to slow down and do some problems, which I do sometimes too. And I definitely would like to help you with some problems Friday. We're off Monday. I'm taking the day off Monday. Next Wednesday, I can help you with problems. And next Friday's a test on chapter 12. You don't have to memorize formulas. I'm giving you formulas for chapter 12. So work on doing problems. Don't memorize formulas.
Just graph something real quick. This is 12.1, and I graphed this on my calculator, and it shot the graph this way. When I went to the solution, the others were pointing this way. So I don't know if that's